Okay, thank you, Sabina, for the introduction. Actually, I'm presenting on behalf of a colleague of mine who is on vacation. I told him Venice, but he still insisted on vacation elsewhere, so go figure. And for those of you who haven't or who have drunk enough coffee, will remark that I have here in the title depleting reservoir. So you ask what's the connection with CCS? But it's again a case that well, to say my colleague or our group went to where we have data, and this is the oil and gas business, looking at the opposite effect, and then we can discuss if injecting CO2 reverses things. Of course, it's not the same fluid, and Al has mentioned a lot of things that we should be careful about. But on the type of stresses, etc., what is happening to the caprock, the reservoir? Is it completely reversible? Well, this will remain as a question for the audience to solve at the reception tonight. So I don't know if the real author is mentioned here. It's Marcin Duda. And I think this ties into, Tony, your last question about the coupling of the poroelastic coupling, how it affects stresses. And it's even more complicated. But basically, if we assume a kind of rugby ball type of reservoir, which we know that all reservoirs are absolutely like that, looking at first depletion, so compaction, intuitively, if we're looking at a point just above the reservoir in the caprock, we will have some vertical stretching. So we expect the stresses to react to a sort of a kind of stretching of the material. But if we look at the flanks of the reservoir, we actually have increase in the vertical stress there. This is due to some arching effect that you kind of it's a lot like the when you drill a borehole, you redistribute the stresses. And in terms of the overburden, then you would probably have a change or an increase in the shear stresses. So most of the time, and that's where the confusion, even with those doing this every day, I'm not doing this every day, so I'm even more confused. But when we talk about pore pressure changes in very almost impermeable rocks, such as shales or caprocks, what is happening there? So mostly at short timescales, at least, things are called undrained. So the rock doesn't see what we're in terms of the fluid, it doesn't see what we're doing outside of the element we're focusing on. But on the long term, on the geological time scale, of course, we see some changes. But still, we get sealing, we get hard hydrocarbon deposits. So it's very slow. So we can safely, for this discussion, say that we have an undrained pore pressure. We don't give the shale enough time to quit itself of the overpressured or underpressured fluid it has in its pores. So you see that this chain of events, if we do something in the reservoir, we change the fluid pressure. It affects the chain of forces between the grains, what we call the effective or net stresses. This in term is like any mechanical coupling has to be felt by any rock on top of it. And if you start stretching the matrix and you don't let the fluid enough time to go out of it or go elsewhere, it cannot equilibrate. So you would also see pore pressure change in the overburden. Now, the thing is that further complication is that, as you see in this cartoon, especially shales have a internal or intrinsic structure or anisotropy, which further complicates. It doesn't just inflate like a balloon, which we assume a lot of times in our models. You'll see that there are some preferential directions, and this has an effect when we try to answer which of the stress components is impacted by what. So you've seen such sketches before. Everything is doing what it's doing. We don't really care about it unless we have some sort of failure envelope criterion that we don't want to meet. So of course, if, as we talked before, if the pore pressure changes in one direction, it will meet sooner than later the failure envelope. If it's in the other direction, it will not. But bear in mind that this failure envelope can also have a cap, and you can have other nasty effects, which we researchers like nasty effects, but we have to admit that most of the time things are safe and we don't need these nasty effects. So, but it's less easy papers to publish. So as we said, we have low permeability, no significant fluid movement, so limited diffusive pore pressure, but we still should see a change in the pore pressure. And these are, I will not spend time with the equations, just this is something that is well known. This is the poroelastic coupling, and we have these coefficients B and A, which are the Skempton parameters. Usually one assumes isotropy, so they are kind of bunched into one double, but it turns out that it's difficult to do it in anisotropic rock. And on top of that, you saw in the first balloon sketch that the type of stress changes are not the same everywhere. So if you want to resolve for the principal stresses, that's the, I think we should have asked somebody from the Biennale, and there's architecture stuff going on, to make the sketches for us. It would have been more explanatory, but suffice to say that things don't align. And then even if you assume some partial symmetry, you have to rotate your vectors, your tensors in such a way that you end up understanding what happens where and how. So here's a modeling workflow that my colleague, actually it was during his PhD, came with. So you get field data, which includes geometry, initial stresses, pore pressure. You do some clever laboratory experiments, which are very time consuming because just getting a whole or a non-breaking shale specimen, if it's a field specimen, is quite difficult. And you try to do all these orientations and look at how the pore pressure changes and the stresses changes doing different stress paths that we will come to. Then you populate your geomechanical model, and then you look at your drilling scenario if it's the case of the depletion, and what happens if you're injecting as well. And then you have all sorts of ways, numerical analysis that can help you with complex geometry. And you can get several interesting things in the end, which is the pore pressure around the borehole induced by the drilling. It could be the changes in pore pressure in response around the design borehole, and the pore pressure changes around the reservoir induced by injection or depletion. So around the reservoir includes also the overburden. So this is the type of experiments that we perform in the lab. As you see in the x-axis, the time is in hours, and it's quite long. So you'd better not have power failure, as we had, I think, in the middle of the Easter holiday. We have, of course, a kind of generator that comes into use, but when you have such lengthy tests, it's quite frustrating. And of course, these stoppages always occur near the 419th hour of the experiment, and you have to restart everything. But that aside, with what we do here is that we determine two of these Skempton coefficients. So it's a kind of, it's not completely wild and random. We can determine two of the coefficients and then kind of populate the others that we want. So you see that the experiments align quite well if you look at this stress path parameter, which is kind of the change in one of the stress components over the other one. And from there, you extract your coefficient, and it was quite um, surprising in a positive way that you have such a good alignment. So possible reason why these data points are so aligned is that maybe the sample was loaded a bit too much before the cycles shown in the previous stage, and it was already plastically deformed. Then it was unloaded, and the 4 cycles are within its new extended elastic range set by the first um, accidental loading. We don't really know, but I mean, when we have nice results, we tend to accept them. 5 minutes, okay. So on to kind of real field data. I hope enough anonymized. Here it's the Lister shale, which is representative for the entire overburden. And the symmetry axis of shales can be approximated by a normal vector of the layers. If the layer is tilted, the symmetry axis isn't vertical, and the deviation from the vertical direction can be estimated from the local tilting. I won't go into very detailed explanation of the plots. That would bore you, and I don't have a clue. But just to show you that getting all these different parameters, remember before in the isotropic case, we only have one parameter to determine, is a bit of a nasty work. So we're looking for a way to simplify the entire process. So using statistics and quite a few data points is one way of doing it, and looking for correlations to try to correlate these different Stanton coefficients to more data points. And you can get some quite accurate approximation of the modeling. So the pore pressure change, the delta PF on the y-axis, using only the vertical stress change that you see on the x-axis. And for the inverse of this B33 coefficient, only 2 parameters are needed. And also here, somehow, there's a correlation shown with casing failures, which is a quite good indicator that at least our model should spot where, if we know there have been casing failures, that it should happen in the areas where the stresses are changing. Yeah, I won't go into these details. I think as a conclusion, we can say that the anisotropic angle-dependent, fully three-dimensional pore pressure change modeling routine, so it's not the pore pressure that's three-dimensional, it's its consequences, is tedious but manageable. And the approximation of this vertical, so you have one axis and of anisotropy between the vertical and its isotropic in horizontal axis. Uses only 2 parameters and seems to be working quite well. And the pore pressure changes can be substantial relatively far from reservoir. So there's no point in doing all of this if you end up saying that, okay, don't worry, model the caprock as an isotropic homogeneous rock. It does make a difference. So the stresses also can differ significantly, and the spatial correlation exists between casing failures and modeled stress changes. So my colleague is quite modest and asks if it really does mean anything. Yes, it does, but remember this is for the depletion case. And actually now when we come and re-inject into the reservoir, the question is if would we recover what we had originally? Is there hysteresis? Could there be damage done during the depletion if we're talking about depleted fields? that we didn't look at or didn't feel because we were extracting fluids. So we don't care if we have some fractures on the flanks of the reservoir. What will happen when we now inject CO2? We don't have answers for that, but we do have models that show that things are not, so there is hysteresis. So you're not reversing everything. But actually, from the very simplistic 2D models that we have, it shows that it's a good thing. It's where we're not destroying any more than what we assume has been destroyed in the depletion phase. So the question is, if there are some leakage pathways, re-injecting the CO2 will probably not propagate these fractures. Those that are there will still be there. There will not be, of course, if you have creep, etc., that's another question. But just from the stress analysis and the stress arching and this type of things, you will not mend these existing fractures. But it doesn't mean that you will propagate them. So, yeah, we need some more research, as we always like to do, let's say. Thank you. I think I will stop at that.